Okay. So, let us continue the discussion of the degree of reaction in axial flow compressor, and this is what we stopped at, that the different velocity triangle for different degrees of reaction. And so, these are one can see how the blade angles that varies for 0% degrees of reaction, 50% and 100%, and what could be the blading pattern or the angles that one get for the. So, this is very important aspect of when you look at the blade design and talking about the degrees of reaction, because these are very important in the sense these dictate the rotor blade design and the loading on rotor blade and things like that. So, another thing just to note here is that we have assumed reversible work done in the stage. So, work done factor is unity, but due to the presence of irreversibilities, actual degrees of reaction will differ from 0.5. Okay. So, for an axial compressor stage in which the change in density is small, so this psi would be approximated at P 2 minus P 1 by P naught 3 minus P naught 1. So, which is essentially the static pressure rise in rotor by stagnation pressure rise in whole stage. Okay. So, this could be very easily shown. I mean it one can just do by assuming just like a flow is approximately isentropic in the rotor. So, if you write the TdS equation, which is dH minus dP by rho, so which gets dH equals to dP by rho. Now, since rho is pretty much constant, one can write H2 minus H1 1 by rho P2 minus P1, and similarly H naught 3 minus H1 1 by rho P naught 3 minus P naught 1. So, we can get H 2 minus H 1 by H naught H 3 minus H 1, which would be H 2 minus H 1 by 1. So, we write P naught 2 minus P 2 3 minus P naught 1. Okay. So, which is that means the degrees of reaction can be also estimated. Now, we will move to another theory called the radial equilibrium theory. So far the dimensions were in mean radius, we have neglected the variation of the proportion, but our u is omega r and our Vz, V theta and P depend on u through alpha. So, all the parameters would be essentially all the parameters will be function of r. So, Vz is uniform, that means radial at the inlet, So, large variation can develop at some stages. So, V theta would be function of alpha r and P r would be function of V theta r, or rather. So, we can check this element for the radial equilibrium theory. Okay. So, this is dz, this is d theta. Now, this distance is r, this is v theta, that is delta m. So, in another schematic, if you look at in that viewpoint, so one can write this side is p plus dp by 2, p plus dp, p plus dp by 2, this is p, this is d theta. So, this distance would be r. Okay. So, we can find out this radial variation. Now, consider a small fluid element. This is small fluid element of mass delta m with tangential velocity component v theta. Now, the force would be delta m v theta square r. Now, from the force balance of this element, which is here, we can write that p plus dp r plus dr d theta dz minus p r d theta dz minus 2 p plus dp by 2 dr d theta by 2 dz, which is rho dr into r d theta dz v theta square by r. Okay. So, essentially here the centripetal force is, here we can write del m is rho del v is dr r d theta and dz. So, forces on the side faces in radial minus axial plane considering the average pressure. So, once we simplify this, we can write p plus dp r plus dr minus p r minus p plus dp by 2 dr rho dr v theta square. So, now further simplification would give p r dp into r plus p dr plus dp dr p r p dr minus dp by 2 rho dr v theta square. So, this cancels out, that cancels out, this is 0. So, in this goes out and this also. So, what we get, r dp equals to rho dp v theta square by r. So, that is what we get. So, here v theta square by r, rho dr v theta square by r. So, what we get r dp rho dp v theta square by r. Sorry, this one would be rho dr. So, then you can write 1 by rho dp by dr equals to v theta square by r. So, that is what your radial equilibrium equation. Okay. So, actual velocity distribution must satisfy this behavior. So, this is important. Now, one can again consider a special case. What it could be is that the any radial direction r, the stagnation enthalpy is given by H naught equals to H plus v square by 2, which is Cpt plus half Vz square by v theta square. Now, since Vr is small than v theta and Vz, what we can write Cpt equals to gamma by gamma minus 1 p by rho. So, which turns out to be H naught equals to gamma by gamma minus 1 p by rho plus half Vz square plus v theta square. So, once we differentiate this one with respect to r, what we will get. So, before we do this, another thing which one can write, that the change in pressure is one stage is small. So, change in pressure in one stage is small. So, which means the flow can be assumed to be isentropic. So, that is an you can assume that then p by rho to the power gamma is constant. Now, one can write dp by dr c gamma rho gamma minus 1 d rho by dr. So, once you do the simplification, so this will get you dp by dr gamma p by rho d rho by dr. So, that is another part of it. Now, we differentiate this guy with respect to r. So, what we get dh naught by dr Vz dVz by dr plus v theta dv theta by dr plus gamma minus 1 by rho dp by dr minus p by rho square rho by gamma p dp by dr. Now, this we write d rho by dr equals to rho by gamma p dp by dr from here. So, if you use that, what we will get dh naught by dr is Vz dVz by dr plus dV theta by dr plus gamma minus 1 gamma rho dp by dr. So, which boils down to dVz by dr v theta dV theta by dr plus v theta square. So, this is another way one can find out. Now, let us assume apart from the regions near the walls of the annulus, the stagnation enthalpy or other internal temperature will be uniform across the annulus to entry to compressor. So, what that happens, d naught dh naught by dr would be 0, since flow is axial or rather predominantly axial. So, small variation in radial direction. So, that means constant work input at all radial, hence H naught will progressively increase in axial direction. So, this is V z d V z by dr plus V theta d V theta by dr plus V theta square by 2, which will be 0. So, again special case, if V z is maintained constant across the annulus there, then we can write d V z by dr is 0. So, which get us back from here is that d V theta by dr equals to minus V theta by r. So, which means d V theta by V theta equals to minus dr by r. So, that gives her V theta r is constant after integration. So, which means tangential velocity is inversely proportional. So, V theta would be inversely proportional to the r. So, condition known as free vortex, constant work input all radials, constant V z all radials, free vortex variation of tangential velocity. So, these are the situation. So, that means constant work input at all radials, constant V z at all radials, free vortex variation of tangential velocity. So, these are all satisfying. So, this satisfies radial equilibrium. Also, this V theta into r constant also satisfies the radial equilibrium. Now, what important is that when we have free vortex design, this requires large blade twist. So, this requires large blade twist in order to maintain V theta into r equals to constant. So, that means high structural stress, which may lead to blade failure, large absolute velocity in the rotor exit. So, that could be another issue. So, that means small pressure rise in rotor, which means small degrees of reaction, but widely used though in axial turbines. So, free vortex design widely used in axial turbine compared to compressor. Now, with that node, we will move to the different kind of efficiencies that one can define for compressor. So, there are three different kinds which actual and ideal work one can do. One is the stage efficiency, which is eta stage, which is ideal work done divided by actual work done in a stage. So, that one can write H3s minus H01 by H03 minus H01. Second, it could be adiabatic efficiency, which is eta c, again ideal work done divided by actual adiabatic work done for whole compressor. Okay. So, this was discussed in already in cycle analysis. So, this differs significantly. So, differs from stage efficiency. Third could be polytropic compressor efficiency, which is eta p c, that means ideal work done divided by actual work done for an infinitesimal step in compression process. So, this is typically your stage efficiency may be with the polytropic efficiency. So, we can always find out a relationship between eta p c and eta c. So, let us consider a TS diagram. This is stage. So, goes from here to there, let us say P naught, this would be P naught plus dP naught. Okay. So, that is dt naught dt naught S. So, there is a incremental pressure rise from P naught to dP naught. So, my eta P c would be dt naught S by dt naught. So, we are trying to find out the relation between eta P c and eta c. Now, for isentropic process, what will happen? T naught 2s by T naught 1 is P naught 2 by P naught 1, which is gamma minus. So, T naught 2s minus T naught 1 by T naught 1 is P naught 2 by P naught 1. So, d T naught S is P naught plus dP P naught by P naught, which is minus 1, T naught 1 plus dP P naught by. Now, if we use the binomial expression for dP P naught, which is smaller than this, we can write 1 plus dP naught by P naught gamma minus 1 would be 1 plus gamma minus 1 by dP naught by P naught. So, we write dt naught S equals to T naught gamma minus 1 by gamma dP naught by P naught. That means eta P c dt naught equals to T naught gamma minus 1 by gamma P naught. Now, when the compressor between two stagnation stages of 1 and 2, if eta P c and gamma constant, then this T naught 2 by T naught 1 would be P naught 2 by P naught 1 gamma minus 1 by gamma eta Pc. So, eta C is minus H naught 2 minus H naught 1, which in terms of temperature, that is T naught 2s by T naught 1 minus 1 by so we get eta C, which is P naught 2 by P naught 1 gamma minus 1 by T naught 2 by T naught 1 minus 1. So, that we can write P naught 2 by P naught 1 gamma minus 1 by gamma minus 1 by P naught 2 by P naught 1, which is gamma minus 1 by gamma eta Pc minus 1. Now, this is what the relationship between adiabatic efficiency and polytropic efficiency. Now, typically eta C is less than eta Pc. So, the difference increases with the increase in P naught 2 by P naught 1. So, with this, if there is a increase in pressure ratio, the differences also increases. For low pressure ratio, eta C is pretty much equal to the polytropic efficiency, which would be also same for stage efficiency. So, this is an important conclusion, or rather important information that one should keep in mind, is that when you have low pressure ratio, then these three different efficiencies which we have got here, stage efficiency, adiabatic efficiency or polytropic efficiency, they turn out to be same. So, one can look at the textbook like Hill-Peterson or any other textbook for this proof for low pressure, but here adiabatic efficiency would be lower than the polytropic efficiency, and this typically this is what happens, but this difference between the adiabatic efficiency and polytropic efficiency will increase with the increase in pressure ratio. So, if the pressure ratio actually increases, then this difference also increases. So, we will look at the other relationship in the subsequent lecture, and we will stop it here.